All right. So what does all that dy dx nonsense mean, first of all? The dy dx nonsense is essentially just different ways of saying the same things. We do a lot of math. So these are all ways that we can write the derivative function. Derivative of y equals f of x, how about? Okay. So we could say f prime of x. That's a great way because the prime reminds you that you have started with the original function and you've derived a new function from the original one. Prime in math just means changed. Okay. In this context, in a calculus context, it means changed in a specific way, changed by differentiation. Okay, so there's one. We can say dy dx. Dy dx looks a little odd, but think of what a derivative means, right? A derivative graphically represents a slope. What is the definition of slope? Delta y over delta x is how you always learned it, right? The slope of a line. So doesn't that make sense then? This is like saying, okay, dy dx is like the calculus limit version of delta y over delta x, where delta now becomes really small, right? So instead of those points being separated and being secant lines, we're pulling them back on top of each other to become tangent lines, right? So really this is just kind of a reminder of how we get a derivative from the slope of a secant line. But that's a really common notation also. And you can also do kind of hybrids of this stuff. You could do something like if I had, for example, if I had y equals tangent x, that's my function, then I could also just write y prime for the derivative. And you'll learn that later. That's just one of our derivative rules. Okay. But the important thing here is just the notation. That means derivative. Okay. You could do things like this. You could say the derivative with respect to x of something. Okay, and then it's like saying this is my y. So say I said derivative with respect to x of tangent x. Well then tangent x is just my y, right? See what I'm saying? And this would just be same thing. Okay, so these are all common ways. All four of these are common ways of writing. Add y prime there. Those are all common ways of writing derivatives. You might even see weird things like in your college textbook where it says things like, oh, what could it do? It could do something like capital F prime, or sometimes they'll even do weird stuff like this. They'll say something like that, derivative with respect to x. That's really bad, though. That would be a bad textbook. Bad idea. These would be the ways you'd most likely see it. Okay? All right, so what I want to do today, then, is you're going to be really thankful for this. This is a great day in calculus because I want to take you from doing the really kind of laborious limit technique for calculating derivatives, taking derivatives, to a much more efficient, you might say, is the calculus trick. The basic differentiation rules just make it really simple. The problems that would have taken you 10 or 15 minutes to do and will take you that long to do on this assignment, you'll now be able to do in 10 seconds. Okay, so there's a much easier, more efficient way of doing this. What we want to do first, though, is we want to come up with, I want to derive the rule. One of these we can get, one of our rules we can get for free. If c is a constant, what does that have to be? The derivative of c with respect to x, which is the same thing as saying the derivative of the function f of x equals c or y equals c. Think what that function looks like. What does the function y equals c look like? It's linear, and there's something important about it. Well, it could be, but if y equals c, what's it look like? Horizontal line, right? Okay. That crosses the the y-axis at c. So what's the derivative of that? What's the slope of that line? 0. So the derivative of a constant is always 0. Okay, there's kind of our most basic differentiation rule. Okay, the next one we want to get to though is this guy. We want to know the derivative with respect to x of x to the n is what? Okay, that would be useful, wouldn't it? We got to find that one on our own. Okay, so we're going to start, whenever we do a proof in calculus, or in anything really, when we do a proof, we're going to go back to the most general representation of the process and apply it to a specific example and see if we can come up with, I don't want to even say the word specifically. We want to come up with a general representation, in this case of a power function, of the derivative of a power function, and see if that's going to distill down to a general answer that's always going to be a pattern, you know, that we can rely on. Does that make sense? So we want to know what is, if y equals x to the n, then what's dy dx? Okay, so we got to go back to our basic limit definition of a derivative. We always start there, and then we'll apply that limit definition to this type of a function. Okay, so what is that again? This is one you guys all know. Limit of derivative f prime of x, or dy dx, is limit of f of x plus delta x minus f of x over as, okay, good. So if f of x is x to the n, what is f of x plus delta x? X plus delta x to the n, right? Everybody agree? So that's just going to be the limit of x plus delta x to the n minus what's f of x?
X to the n.
Obviously, if we plug in, we try to evaluate this directly, of course, we get 0 over 0, right? Okay, so the question really comes down to, how do we treat this? How do we treat x plus delta x to the n? Okay? So, there's a couple ways we could go on this. Did you guys learn the binomial theorem last year? For expanding a binomial? So you know how to expand like a plus b to the n, where n is arbitrary? Okay, well, that's okay. We could use that formula, and all you have to do is just Google the formula if you want it. But that's the one. That's the one. Let's do this a slightly different way, though. The way that might be a little more satisfying. We could use the binomial theorem, and you'll see in a little bit how we could use that, and it would be totally fine. But let's do this using, because I kind of want to reinforce it, let's do this using the Pascal's triangle trick I showed you. Okay? So if we go, we want to be able to expand x plus delta x to the n. Well, we could do this for finite values of n pretty easily. But we're going to see if we can come up with a pattern pretty easily that would essentially represent the first few terms of the binomial theorem, right? The problem with this, of course, is going to be n could be arbitrarily big, right? So what if n were a trillion? The binomial theorem would be kind of a pain to use, and obviously Pascal's triangle would be a huge pain to use, right? It wouldn't be practical at all. So either way we slice this, we're going to have to come up with a tricky way to handle an arbitrarily long expansion, but it's going to work out in a really cool way. You'll see. So our coefficients, remember, are just 1 like this, right? What goes there? 2. How come 3?
Okay.
Adam, okay. Let's do one more. Good. Okay, so this is the row that corresponds to n equals 0, right? This is the row that corresponds to n equals 1, n equals 2, 3, 4, 5. Okay? So can we see, and we know what these mean, right? For example, if we took, let's just take this row right here and let's represent it as a binomial, right? So in other words, we could say that x plus delta x to the 4 equals what? 1. What did we do with that, remember?
1.
These are just the coefficients. What do the factors look like that go with the coefficients in each term? X to the 4, okay. Delta x to the 0, right? Plus 4x cubed, good. Delta x to the 1, right? Plus 6x squared, delta x squared, right? Plus 4x delta x cubed plus delta x to the 4th, right? Okay, so can you tell me then, can you see kind of a pattern where we could maybe take the first, let's just say we're going to take the first 3 terms, or 4 terms, and we could build those based on the value of n, come up with a formula that would work. The first one's always 1. What is going to be the next coefficient? How does that relate to n?
The same number as n.
It's the same number as n, isn't it? Everybody agree? So if we wanted to generalize this, you could ever see where I'm going with this? So if we wanted to generalize this, then we could say that x plus delta x to the n equals 1 times x to the n, right? Plus, you told me that the next coefficient was just n, right? N times x to the what?
N minus 1.
N minus 1? Everybody agree? Times delta x to the 1, right? And that's fine because remember the sum of the powers of the factors has to always add to n, right? Okay, so what about the next one? What about the next, what's that? That one's a little trickier, isn't it? How are you going to get that one out of there? So for n equals 2, we get 1. For n equals 3, we get 3. For n equals 4, we get 6. What in the world? What's going on with that?
You add.
Well,
Yeah, you add.
I want you to think about that. Think about what's going on there. See if you can see a pattern.
You add them because to get from 1 to 3, you need to add the 2, which is the n. So you add, to get from 3 to 6, you need to add the 3, which is the n.
Okay, but to get from, like, see, I got to be able to get from, somehow I got to be able to get to this number, right, from that number, right? The value of n somehow has to predict the coefficients.
You just add the one above it.
So this one is a 2, right? 2 gives me 1, 3 gives me 3, 4 gives me 6, 5 gives me 10. That's weird.
But it's like, no, it's like
So-
you add the 1 and the 2, you get 3. You add the 3 and the 3, you get the 6. You add the 6 and
Oh,
the
I
5,
see what
you
you're
get
doing. So
the
you're,
10.
okay, good. So you're saying, say it again, you're saying you add the 1 and the 2 and get 3, okay?
Because the n is the 2. Because, like, for 1, when you have n equals 2, you get 1. But and to get the next one, you just add the n value to
Okay, so you're saying you add the n value to this number.
not that.
To which number?
The
Come show me. Because I'm just trying to see, I know what the answer is. I'm trying to see if this is going to get you to the answer.
no, it's, you add these 2 to get 3. You add these 2 to get the 6. You add
Oh,
these 2 to get the
okay,
10.
that's interesting. Okay.
Because n equals 0 plus n equals 1, it gives you 1, and then you add the 2 to get to 3,
Ah.
and then 3 to 6.
Okay, now how's that going to...
Probably wrong, but it's a good idea.
So you're saying, okay, you're saying you add...
I
still
didn't
not
even
seeing that.
touch the red.
I guess I'm still not seeing that. Say it again, I'm just trying to see how that pattern's gonna work. You got it?
Well, so you got 0 and the 1, 0, and then you add the next n, so that gives you the 1. And then you're gonna add the next n, which is 2, gives you 3. Add n 3 is 6, 4, 10.
Okay.
So next will be 15. I don't know if that's right.
So let me see, so you're saying you add n
It is
plus n plus 1? Oh, okay,
I think so.
but, yeah, that's what you're saying, right? Ah, but you're
Yeah.
basing it on this number.
Yeah.
So that number, we still don't know how to get that number.
Which number?
Because you're saying you add this number to this number to get that number, right?
Yeah.
Okay, but see the problem with that? You're right, you see a pattern, but the whole here is that pattern works, but how did we get that number?
Because that's the.
See what I'm saying?
Yeah.
It's like a snake swallowing its tail.
Because it's the n. Okay, wait. So when you have the n of x, yeah, the n you have in front of the x is the same n that is. I can't explain this, but it's like when for the red circle,
Mm-hmm.
you have the 1. And the,
Okay, but I don't have the 1 because I don't know how I got that one. You see what I'm saying? I know what you're saying,
yeah.
but you see what I'm getting at here? You see a pattern, but that pattern presupposes that we know how to get this number, right? But we don't, right? Because this scale mathematically is just going to go. This column's going to go forever, right? We got to know we have to have some way that we can generate those numbers though. So I'm going to steer you in a little different direction with this. See if you can come up with a way, and this is just kind of a fun puzzle. See if you can come up with a way that these n's could generate those values. Okay? Is there a way that these n values could generate those? Is there something I could do consistently? And there's no magic for finding this. It's just a puzzle. Like how could 4 give us 6? I mean, you could do things like, 4 plus 2 obviously doesn't work, right? That's not going to be adding something. So maybe we can multiply something. But what about like 4 times 4 divided by, that doesn't work either, right?
Times 1.
Well,
It's like
you could do n times 1/2. Well, like I don't know how to
Ah,
you do n
okay.
times 1/2, that gives you 1. And then it's times by 1, and then 1.5, and then 2.
Okay, now interesting. Okay, so what if we did something like, what if we multiply n, because you did see something here, right? You saw that there was a link between the n equals 3 row and the n equals 4 row, right? Okay, so what if we multiplied the value of n by the previous value of n and see if we can make a relationship there? Okay, does that make sense? That might be a plausible thing to try if you can find this relationship where there's a vertical relationship between the rows. You see something?
Oh, well, you'd multiply like the n by the one preceding,
Okay.
divide by 2.
And divide by 2. That's it, isn't it? That always works, doesn't it? Everybody see it? It even works here. Because then we'd get, to get this guy here, we'd multiply, to get this guy here, right, we'd multiply 1 times 0 divided by 2 is 0, and that's why it doesn't show up. Agreed? Okay, that's it. That's the pattern, right? So how would we say that? Well, then isn't that just, you tell me, how do I write that? N times, times what? N minus 1 over 2, right? Make sense? Okay, times x to the
n minus 2.
n minus 2 delta x
The n plus 1. Or the n. It just be like.
What's delta x have to be? These have to add up to n, right? So delta x to the second, okay? Now the next one's tricky. The next one's really tricky.
What was the last one?
Yeah.
The last one was pretty tricky, I agree. The next one's like ultra tricky. How am I gonna get a 4 from an n equals 4? Okay, my hint is this one involves, as you might expect, if we continue that last pattern, it's going to involve the previous n value and the one previous to that. Right, so now we're trying to generate, just so we can make sure we're all on the same page here, we're generating the green diagonal, right? Whoops. Oh, whoops. That's what you probably want to do. Okay, so we're trying to generate.
There you go.
There we go. All right, I'm trying to generate those diagonals, right? And I'm trying to generate those, so I want to generate the value of 4 from those 3 values, for example, right? And I want to generate the value 10. I'm going to really color code this. What's that going to be? That's going to be weird shade of blue. From those 3, right? You see it? How can I get 4 from 2 times 3 times 4? And keep in mind, it's probably got to be a product, doesn't it? Right? Because sums aren't going to progress in the right way. Right? It's got to be probably a product. Everybody see it? So I'm going to use the 3 green circled letters to get that, numbers to get that. What's the product equal
All 3 of them is 24.
24. Okay, well, how do I get from 24 to there? Divided by 6. We'll see if it works again. 3 times 4 times 5 is 60. Divided by 6 is 10. How about up here? 1 times 2 times 3 is 6. Divided by 6 is 1. Ah, okay. Are you getting it? So we're going to follow kind of a pattern like that. And there's even a way that we could predict what the number on the bottom is going to be, but we don't need to go there. So this is enough. This is good enough. That's a long enough list for us to do our thing. So the next one is n times n minus 1 times n minus 2 over 6, right? Times x to the n minus 3 delta x cubed plus dot 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 all the way over to, what's our last term? Well, it's
X to the n.
X, well, delta x to the n, right? Right? Okay, so we can actually do what we need to do with that. So let's take the limit of this. Okay, let's apply our limit formula with this, right? You have to write small. So dy dx, if this is y, dy dx is the limit of that, right? Everybody agree? I'm going to get the limit of f of x plus delta x, which is x plus delta x to the n minus x to the n, right? All over delta x, as delta x goes to 0, which is going to look like, oh boy, you ready for this? The limit of this guy is going to be x to the n plus n x to the n minus 1 delta x plus n times n minus 1 over 2 x to the n minus 2 delta x squared plus, I'll do one more, n times n minus 1 times n minus 2 over 6 x to the n minus 3 delta x cubed plus yada 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 delta x to the n, right?
You want to start this whole thing?
No, I mean you don't have to. You can just watch it.
You are recording this, right?
Yeah.
Okay.
So all that minus x to the n, right, over delta x.
Oh,
Divided by
as delta x goes to 0. Yeah. Okay, so do you see anything, that's a mess, right? But do you see anything good that we can do there in that top row, the denominator?
First and last.
So what can I do?
Cancel out the first and last. The X,
Ah,
X to
okay.
the end.
Yeah, look at that. I can cancel out the x to the n and the x to the n. Okay?
Oh,
So what do you notice about all the rest of those terms?
delta X.
They all have powers of delta x, right? So what could I do?
Take out delta.
I could take out a delta x. How about that? So I could rewrite this then as the limit of delta x times what's left over. What does that term give me?
N minus 1. N times minus 1 over 2. X n minus 2. Delta x. Go.
And that's 1. And that's 2. Or 6. X. To the N minus
X.
2.
Squared.
Plus yada yada yada.
Plus yada yada yada.
X. N minus 1.
Yeah.
Right? What can we do? How many factors are in the numerator?
How many factors?
Mhm. 2. Delta x times that big thing, right? That big quantity. I can cancel like factors.
True. Right over 1.
Away goes the indeterminacy. That was causing the 0 to 0, wasn't it? Delta x was the offending factor, right?
Delta x.
So now I can take my limit. Well, what's going to happen to all but one term in that expansion?
Go 0.
They're going to go to 0. Yeah. Everything with a live delta x in it then, after we cancel out the factored one, is going to go to 0, right? All those go to 0, and we end up with only one surviving term, and so that's the answer. How about that? Isn't that cool? That we just did that?
Oh, dumb.
Pretty amazing, right?
Oh, dumb.
So the answer is
So the answer is, yeah, let's summarize. So the answer is, the derivative with respect to x of x to the n, what we ended up with, right, was n x to the n minus 1, was that one surviving term. So that's our general power rule for derivatives. Okay? Make sense?
So it's just a big proof.
Yeah. But that's the consequence of that big proof. Now we've got a formula that's going to make life so much easier, right? Okay, so let's do one more thing with this then. Let's say, what if we want to do something like this? What if I want to do the derivative with respect to x of c times f of x? What am I going to get? I'm just going to get, aren't I going to get, I'm going to get, when I do my limit here, right? I don't even want to write the whole thing out. Would you agree that I'm just going to get a c as a part of my function, right? Does that make sense? What can I do if I have a constant inside a limit?
You can take
Pull it out in front, right? So without me spending 15 minutes writing this out, are you guys okay with the idea that what we're really just going to get here is c times f prime of x?
No, Mr. Roy, you have to do the whole
You want to do the whole
proof
thing?
again.
So the moral of the story is, when we take the derivative of a constant times a function, the constant we just pull out front, right? We only differentiate the function. Okay, so then we can weave these two together into a more general form of the power rule. And we could say the derivative with respect to x of c times x to the n is what?
C times C and
Yeah, how about that? So now you can do, it would have been a real pain to take, for example, the derivative of x to the fourth, wouldn't it? Right? Easy now. what is, if y equals x to the fourth, what's y prime?
4x to the third.
What if y equals 11x to the fifth? What's y prime?
In D5, 55x to the fourth.
How about that? So what are you doing? You're just taking the exponent down in front and subtracting 1 from the exponent, right? Easy, okay? What would happen if I did something like this? What if I said f of x equals 2x to the fourth minus 3x squared plus 2? How am I going to deal with that derivative?
Come in chunks.
It's going to come in chunks. Because the limits go in chunks, don't they? Right? If we were to do this the long way, we would be taking limits of this function at x plus delta x and x, right? Okay, but I know that if I take the limit of f of x plus g of x, right? That's just equal to the limit of f of x plus the limit of g of x, right? So what that tells me then is, this is good for us. When we differentiate a polynomial or any string of terms, we can differentiate term by term. Each derivative, or each term becomes a simple derivative, and we can just string those derivatives together, right? So what is, if that's our function, what is f prime of x?
So we got 8x to the third minus 6x plus,
Plus what? Well, we know that one, but we can also, that's x to what power?
1.
Right.
0.
Okay, so then what am I going to get from the power rule?
So you can't have an negative sign.
Well, I could, but I'm going to multiply by 0 anyway, right?
Yes, it's 0.
So it's 0. But we knew that anyway if we go back a couple slides, right? We said, right there, derivative of constant is 0, right? Yep. That make sense?
Yes.
Ooh, that's pretty good stuff, huh? Yeah. Huh. How much time we got here? We're on a weird schedule. 2 minutes?
I think so.
Okay, well, that's a great place to break.
Yes.
Okay.